So this next presentation is also on automatic differentiation by Tom in the context of the Accelerate EDSL for Haskell.
Yes. So given that this topic is fairly similar, or at least in a similar direction as the previous talk, I will be skipping over a few bullet points in my slide, but it should be all right. So what we're talking about is reverse automatic differentiation for Accelerate, which is a different language than Dex, obviously. And this slide is just a bit of a summary of why you would want automatic differentiation in general, which was also hinted by Adam a bit, which is basically that there's a number of domains that allow you to specify things, specify certain subroutines using programs, for example, machine learning, but also Bayesian statistics. And you might want to, if you want to do some kind of optimization or inference on those things, you might want to differentiate those. And in practice, the kind of differentiation that you need is that you need gradients of functions, and the variant of automatic differentiation that you then need is reverse mode automatic differentiation. Hence, that is the variant that I will be looking at. And we're doing this on a functional array language for the reasons that should be obvious to the people in this workshop. And the functional array language in general, in this case, is Accelerate. And let me briefly, for the people who aren't too familiar with Accelerate, tell a little bit about how that works. So this slide will describe the core language of Accelerate, which is slightly different from like the surface language of Accelerate that users program in. But yeah, it's the language that a compiler transformation will work on. So it is a purely functional second order array programming language. And this second orderness is as Sven Bodo has alluded to earlier, is a choice that Accelerate makes. And that is that you don't have syntactic nested parallelism, but instead you need to use rank polymorphism. So we have like the standard array of parallel constructs. You have the standard like functional programming situations. This is a small example program, but crucially, like for example, in this function here, this takes two scalar arguments, and you couldn't do any parallel operations within here. The compiler will reject that. Because what instead you should do is you should have an n-dimensional array and do this implicit mapping that's going on, right? These scalar functions are in Accelerate called expression functions, and they like at some point in the compiler they actually live in a different programming language, so to speak. They live in the so-called expression language, which has basically first-order arithmetic expressions and the expected things. And crucially, one thing that it has, and what you kind of need for certain applications, is that it has array indexing. And that means that you can, while you can't have parallel operations within an expression, you can, of course, index a free array variable at a particular point, because that is, well, it's not a parallel operation, is it? And this, I wanted, in this talk, I'm going to focus on how to differentiate that particular operation, because that comes back to bite you when you try to differentiate programs. So again, we're computing gradients, which is a collection of partial derivatives of the function result with respect to all its input values. So for example, just to give an example of this that it should be easy to understand, this is a program that takes an array and computes the sum of squares of that array, which is illustrated here in some mathematical notation. So what's the derivative of it, or what's the gradient of this? It is the partial derivative of the function result, namely the sum of squares of the input, with respect to every single input argument. And the derivative of the sum of squares with respect to one variable in that sum of squares doesn't have anything to do with all the other elements of the input. It's just 2 times that element. Why? Because the derivative of x squared is 2x. So you can write down this gradient program like this. And this could, for example, like be the result of this linearize plus transpose procedure that Adam has described. but that is just like one implementation of doing reverse AD. You can make the program slightly more complicated by adding this array indexing in here. And suddenly you have this kind of scatter going on. And how exactly you end up here is something that I will be explaining. So let me briefly, like what Adam has been discussing in the previous talk is to some limited depth how you do forward mode automatic differentiation and the fact that there is reverse mode automatic differentiation. And I'm going to explain a little bit more about how reverse mode actually like works as a program transformation. There are of course like different ways to implement reverse AD that are not as a program transformation, but I'm going to focus on this particular variant. So suppose, for example, ditch erase for a moment, and suppose that you're working on a simple scalar language where you have a function that takes two inputs and computes this formula. So you can write this as a data flow graph, and we're going to do the exact thing that Adam has explained. We're going to reverse the data flow, but we need some values from the original computation. So the first thing that we're going to do in the result of this program transformation is we're going to compute what is called the primal values. We're going to just compute the function as usual, but store all the intermediate values somewhere. And then in the second pass, we're going to have this dual pass, which goes in the other direction. What we're going to do is, remember at the end, we want the gradient of this program. So what we're going to do is for every node in the data flow graph of this function, we're going to compute the partial derivative of the function result with respect to that node. And then at the end, what we will end up computing is the partial derivative of the function result with respect to all the inputs, because those are also nodes in the control flow graph. And that is exactly the definition of the gradient. So the first thing, the partial derivative of this node with respect to itself is, of course, just 1, because that's basic derivative logic. Next, it gets slightly more interesting, because the partial derivatives of addition, like things like this, are just 1. So that means that if you want to compute the partial derivative of the argument to an addition operator, then you can use the chain rule, which I write down like this, to say that the partial derivative of some later result, namely the end result of the function, with respect to some variable x, is the partial derivative of the end result with respect to this addition times the partial derivative of this addition with respect to x. And because this thing is 1, we know that it is just equal to the partial derivative of the addition. So we can copy d6 over to d5 and d4. Multiplication is slightly more interesting, because the partial derivative of a multiplication with respect to one variable is actually the other variable. This thing is this thing. So what ends up happening is that, for example, if you know the partial derivative of node 4, stored in d4, and you want to compute that value for node 3, then you're going to take the partial derivative of node 4 and multiply it by the original value of node 2, which is exactly what I'm writing here. Similar for node 2. And the final interesting thing is that for node 1, we have 2 like outgoing connections, where I see these double arrows, 1 arrow here. And both are going to add like contributions to the partial derivative of node 1, and both are just going to be added together. And this is a general concept in automatic differentiation, in reverse automatic differentiation, that you get this addition over here. So and this is a program, and this program of course computes among other things d1 and d2, which is exactly like the gradient. So you can generalize this to function to a language that has some array operations, and you can do the exact same kind of thing, where you can differentiate sum to a replication of the partial derivative, for exactly the same reason that you can copy d6 here over to d5 and d4, and you can differentiate through this map operation by combining the the incoming partial derivatives, the incoming adjoints, as they're also called, with the original inputs, and then you write down the gradient of this expression function over here. So this is all well and good, and on the next slide I'm going to get into some difficulty. So this slide you've already seen. This is the Accelerate core language summarized. The green parts. So this works better. So basically, this part, this is supported in our implementation. We have an implementation of the algorithm that I'm explaining here. We have some kind of partial, like easy cases support for a fold, an associative reduction, and the easy cases of a scatter. But there are some other cases that are definitely not supported. We don't have a derivative of scans, for which I am very much looking forward to Adam and team's approach of doing that. And there are some other basic array operations that we don't support, but those are slightly less common. We also don't support sequential loops, which I will get to later. But we do support array indexing. And how? I'm going to show you. So this program you already saw. So let's add some array indexing, right? So this is a more complicated program, which contains some array indexing. This syntax means take the array B and index it at the index, in this case, 2 times I. So if you differentiate this, like in exactly the same way as we did here, you might end up with something like this, where you compute the primal values, like let's just explicitly add some node IDs. So we can compute the 4 intermediate values of the primal computation, and then we can compute the adjoint values, the partial derivatives of those. But the crucial thing is that computing the partial derivative of this map is kind of difficult, because how is it contributing to the result? It is contributing to the result only through the usage of this variable b, which is here. You don't have a nice combinator that you can just differentiate as a whole, like write down the derivative, fill in the components, and there you go. You can't apply this kind of generalized version of the MATLAB way of differentiation, if you will. You have to do something more interesting, and that's basically this slide. So remember, we had this array B, and we did this generate, and this generate produces a new array. So what does it produce? It's a generate or build in some languages. It builds an array of size 3, where at each index I, the element that is there is the array B indexed at the index 2 times I. So assuming that B is long enough, assuming that the program makes sense, this is what happens, right? This is what it ends up computing. And that's all well and good. In the dual pass of the transformed program, what we have is the partial derivative, the adjoint of this generate call of this size 3 array. And what we want is the adjoint of this array B, which supposedly contains like the adjoints of the values, right? That's what we should compute, but we have this one. But we know what's in here. We know that in the primal there was B0, B2, B4. So we know that here, assuming like that the rest of our differentiation machinery is doing its job, it should have the derivative of elements 0, 2, and 4 of this array B. So how are we going to construct this DP? Well, just by putting the values where they belong. And the rest apparently don't contribute at all to the result, so the adjoint can just have 0 there. And this is why it is a scatter, because this original function was really a gather operation. And when you dualize that, when you reverse the control flow, you also kind of reverse the data flow, and a gather becomes a scatter. And a permute is how Accelerate notates a scatter operation, where if you have a write conflict, so if multiple values go to the same destination cell, we want to add those. Why do we do that? Because here, if you in the primal had some outgoing arrows, if B0 was also used in this next cell, then in this next cell you would also have an arrow here back to this cell. And you would have 2 elements ending up here, and you want to add them because it is a sharing of values, and sharing becomes addition in the dual in reverse AD. So on right conflicts, we start with an array of zeros, and we scatter onto the array of zeros. The values that we scatter are the incoming adjoints from the generate, which is precisely this array. And we scatter the value at index I to the index 2 times I, where this expression 2 times I is precisely this expression. So you can kind of see how this at least somewhat generalizes. And this is fine, right? So in this derivative of the program, we can fill in the permute, and it works fine, and it gets us a derivative. So this kind of shows how array indexing becomes a permute or becomes a scatter, and it gets more interesting if your program becomes more complex. If this expression function this expression function contains an array indexing operation at the top level without anything containing it. If you have something more complicated like this that contains it inside some larger expression and inside some conditional, maybe even, it becomes more complicated, and you might have to do some more bookmarking, like, was the indexing operation executed? If not, we might not even be allowed to do this scattering operation of this particular cell because it might be out of bounds or something. So there's some bookkeeping to be done, but this can be generalized. And that at least concludes my story about this about array indexing for now. So I just wanted to share that we've done some preliminary benchmarking of the implementation. It's implemented as a broken transformation in the fork of the accelerate compiler, and we benchmark using the GMM and the BA tasks of the AD bench suite, which is a benchmark suite of a few programs that are taken from like real world situations that it might be useful to do AD on, and there are a couple implementations of those particular benchmark tasks in existing AD frameworks, so that it is easy to compare a new implementation with those existing implementations. Because quite a number of those existing implementations only work on the CPU, and because of some technical issues, the benchmarking is run on the CPU. I just want to stress that there's no GPU involved here. And the two benchmark tasks that we implemented, one is a Gaussian mixture model fitting process, which is it's really a test of the reverse AD algorithm, because there's lots of stuff going on, and it's a fairly complex data flow graph. And the other task is a bundle adjustment, which has the peculiarity that the Jacobian of this operation, so the matrix of partial derivatives, is very sparse. What this means in practice is that really instead of differentiating the entire program as a whole, the entire data parallel program as a whole, you want to do an element-wise operation, and within that element-wise operation, you do differentiation of a scalar operation. And they have wildly different performance characteristics. So I'll show you the results in a graph. I will briefly describe what I'm showing you here. So this is a log-log plot, where on the horizontal axis you have the number of independent variables in the input, so basically the size of the input, and because of the characteristics of the program, you expect stuff to be kind of linear in here. Because the vertical axis is the running time in seconds to compute like the gradient. So this graph is how we do, and without further knowledge about the task that tells you basically nothing, I'm going to add a few other implementations. This is how PyTorch does. This is how two kinds of TensorFlow do. This is TensorFlow Eager, and this is TensorFlow Graph. These are two versions of a manual implementation in C++ that do not use any parallelism at all, but also do not use any automatic differentiation. It's a manual derivative. So it's kind of a reference implementation in the framework. There is also a an actual AD framework for C that can do some kind of broken transformation, and with some manual scaffolding that can produce an implementation that is quite fast. That's this one. There is an implementation in F#, which is a bit slower, but also decent on this graph. And there's a final one that I just want to show for fun. This is a finite differencing implementation, which is completely different to reverse AD in that it actually increases computational complexity from linear to quadratic in this case. And you can see that because the line is significantly steeper, about twice as steep, in fact, in this log-log plot, which means that it is indeed quadratic. So what you see is that this one that's cut off here because it runs into a time limit of the benchmarking framework. But more importantly, our implementation cuts off here not due to any kind of time limit, but because we have a very significant memory usage, and basically we run out of memory. So this is an existing problem in our implementation, and we're still well, working out how to fix that is future work. The next graph is about this BA task, which has very much parallelism and is differentiation of scalar level functions. So we are over here, which is kind of decent, except this is our single-threaded performance. If you actually let us multi-thread, then we end up over here, which is, well, good enough given the other implementations in the suite. So brief summary, this is a very pragmatic reverse AD algorithm, and I say that in comparison to other like combinator or categorical kind of ways of doing automatic differentiation on languages. And the thing that I want to emphasize is how to do this indexing kind of thing, and to show that like this kind of innocuous scalar level construct, when you kind of do that in reverse, it suddenly gets blown up to a full data parallel scatter operation. But there are, of course, some open questions, some that I alluded to earlier. We have a memory usage problem. We don't have a derivative written out for sequential loops. There is, of course, parallelism, but we don't have like actual sequential loops because this has some memory allocation issues for GPUs. Because we do want to at least support a GPU target for accelerate. General derivatives of more primitives and some checkpointing thoughts that I can expand on if someone is interested. So that's the end of my slides, and I invite any questions. I do have some suggestions if you don't have questions. Thank you.
Okay. Well, we have two questions, and feel free to ask more. So the first question is, what is a first-order arithmetic expression?
A first-order arithmetic expression is an expression that contains the standard arithmetic operators like plus, minus, times, divide, and also any kinds of standard transcendental floating point operations that you might want to support. But crucially, there is no parallelism involved. So while you may use n-ary tuples if you want, that n in the n-ary tuple should be a compile time constant. So only like actual scalar operations.
All right. The second question is mine, and I didn't phrase it very well, but this way of handling array indexing in your reverse mode transformation, does that preserve the asymptotic cost of the original program?
I guess you can ask that question both in terms of like actual work and in terms of parallel span. In terms of work, well, both actually. So like the standard kind of scatter. I believe like the corresponding function in Futhark to permute will be reduced by index, if I'm not mistaken, which usually, if it in the good cases, is doesn't have any work beside doing a constant time operation per element that it is scattering. That runs into problems if you have lots of conflicts or something. But that is yeah, basically the same kind of provisions that you have there apply here too.
But what about creating the target array? I mean, is it sparse? Does permute create a sparse array in the places where you don't write?
Permute, that is a good question. Permute does not create a sparse array in Accelerate, at least not currently. So that means that to actually, yeah. So you might have some array allocations that get introduced, and if you get unlucky with Fusion, then some of those allocations may definitely persist. But I believe that can still be a constant factor slowdown.
Okay, thanks. So the next question is from John Hughes, who's asking, your array indexing was with indexes that did not depend on the data in the array. Would it be a problem if they did?
Very good question. What you're basically saying is that my example is bad, because due to the fact that the indices do not depend on the data in the array, you can actually do something slightly more simple than this, actually. We support full dependency of the array index on the data in your program. And this works unchanged.
Okay. What's the reason for not supporting sequential loops? Is there some limitation of Accelerate that makes it difficult, or is it just not implemented yet?
Accelerate actually has like two ways of having sequential loops, because it is split in this array language and this scalar expression language. It has a separate looping construct both in the array language and in the expression language. If you have an array level loop, which is an unbounded loop, it's a while loop. What you could do as an implementation, which we have not implemented, but which you could do, is so the problem is the unboundedness of the loop. If you know the number of iterations that your loop is going to take, then you can allocate an array of destination values in the primal case, where you can store your temporary values, and you can kind of scatter them in there, hoping that in-place updates do the right thing. If you have an unbounded loop, then you have to kind of pre-allocate an array, and if it gets filled, you have to resize it or something, which you can do, but it's annoying, and we definitely have not done that. What gets more annoying is if you have a loop in the inside a scalar expression function, because then you basically have lots of loops in parallel, which might not even have the same amount of iterations. If they happen to do so, they can kind of try to split it out so that you can do the same array parallel operation where you scatter the values into a destination array. But if you don't know that, if the number of iterations vary, then you have some kind of non-regular parallelism thing going on, which I don't know how to handle.
All right. So last question, I think it's similar to what you answered before. What kind of indexing do you allow for indirect accessing as well? Can you always statically decide?
Yeah, so yeah, we allow any kind of indirect indexing. You can use any kind of values that you want in deciding what index to index on, even the result of other indexing if you want. What is, I guess, an interesting question is reflecting on how you can speed up the implementation or make the transformation better if the indexing is actually not as dynamic as the general case. And there might be something that you can do there, but that's not something that we've looked into yet.
All right, thanks. We are out of time and out of questions, so that's great. Let's give another applause while I kick Tom off the stage and invite the next speaker.
Thank you.